All right, so welcome to today's session, and today's topic is going to be really something nice and simple: linear superposition, a concept that we've already discussed and we know holds. We've discussed it sort of in general terms. I've demonstrated it briefly in one of the basic notebooks, just to remind you. But yeah, I want to dedicate a whole notebook on it, and the reason for it is simple. It's such an important modeling concept that I want to make sure I solidified it for you. And that when you walk away from this course, this is one of the big modeling tools that you have at your disposal. And so when you think about what linear superposition means in a finite element context, especially when you talk about the linear elastic finite elements, is linear superposition means when you solve one problem, you've solved lots and lots of problems. Okay? The reason for it is, if I've solved one problem, I can change the load at exactly the same location, different magnitudes, and I can tell you what the answer will be without having to resolve it. Okay, I can change the Young's modulus of that material and tell you what the answer would be without having to resolve it. Those are just two simple examples. If I've solved multiple FEMs with loads at different locations, I can then have any sort of linear combination of those loads at those locations and tell you what the answer is without having to resolve the FEM. This is really important. So this is a way that you'll save lots of time and energy, especially in the context of global warming nowadays. You don't want to do unnecessary analysis. It does waste kilowatt hours. And the other aspect is it saves lots of time. If it took you 3 days to do a finite elements analysis of a large linear elastic structure, because by nature maybe it was a fairly involved solution that you had to go and compute, you can actually infer lots of other solutions that without having to resolve them, based on linear superposition. So this is really the context of what it's about. This is why it's so important. And also, you'll see when we start doing symmetry and antisymmetry, it's one of the key concepts that allows you to really extend your ability to model when you want to try and reduce problem sizes using symmetry to make the problem smaller. It's one of the key things that you would like to be able to do is essentially linear superposition gets combined in there to give you some additional modeling power. Okay, so that's not that well known, but it's very important that you just take note of that. Okay, so first off, confirm that we're going to just confirm that the linear superposition holds. So we've already done this. We're just going to reconfirm it. Just make sure we're comfortable with that. Ability to use a linear superposition to calculate the solutions for loads applied at once from solutions of loads applied individually. So that's really if you have multiple solutions, we can actually combine them in that way. Ability to use linear superposition to calculate the solution for a load applied at one magnitude from a solution of a load at a different magnitude. Okay, so this one is one that you can easily do your own. I'm not going to do explicitly in this notebook, but this is what I would like you to do. Just do any solution, multiply the load by a certain number, and you can imagine what's going to happen. You're essentially going to multiply that displacement with that same number. If you double the load, the displacement will double. If you half the load, the displacement will half. This is what the consequence of that would be. And you can easily see it. Ku equals to F. So if I say Ku equals to F, that system is what I've solved. Then I can say K times 10U equals to 10F, because I just multiply the 10 in on both sides and the equations still hold. Okay, so that's important to understand. And then the last one is the ability to use linearity to calculate the solution to a problem when the material has elastic modulus at one value from the solution when the material's Young's modulus was another value. This one I'm going to do explicitly, and there's some question I'm going to ask you: does this hold for Poisson's ratio? And I think most of you already can infer what the answer would be for that, but this is just to make sure that we reflect and understand why we focus on Young's modulus. Okay, so steel bar, 210 gigapascal, 1 millimeter thickness, constrained by rollers, as is the problem that's outlined here. We're essentially going to be calculating what is the displacement field, the full displacement field. So I'm going to do linear superposition in the context of the full displacement field here, but we can just verify and things do make sense. So we do a hand calc, determine what the stress and displacement is that the bar experiences using the MAW227 hand calc. So this verification I'm doing to you. I'm not going to do this. This is something that you should be able to do and say what is the displacement that you expect to see. Okay, then, so this is a really trivial thing to do, but I want to make sure that you are comfortable and have enough confidence to do this on your own steam. Okay, so essentially when we get to this point of having a launch FEM, we're launching this file Q8 pull. So what we see is this bar is 8 mil wide, 2 mil high, 1 mil thick. So a plane stress analysis must be going to be quite appropriate for this kind of modeling here. So here's the one that I want to open, Q8 pull. So this is this one. You can check here what's going on. Plane stress with the elements, the rollers, and the one prescribed node in X as well as in Y, Young's modulus, Poisson's ratio, the thickness, and then consistent node loading that we apply on the right hand side. So that you can see 1/6, 2/3, 1/6 distribution that we see there. Okay, this is all good and well. So now we can move on and say, fantastic, let's solve this. So we run this notebook, solve it, and then we store the answer as U100. Okay, so you can go and check what the answers are here and see whether they make sense. You can also put the magnification factor if you want to specify it. And then, yeah, so here you can see what is the expected solution that we want to see. If we look at now, if you print these values here, boom, what do we see here as an answer? 1904776, 190471905. And so this is pretty much spot on with the hand calc. Just double check something quickly if I make this. Change it to plane strain. You can check now what's going on. If you do plane strain, you can see how much different the answer is. Look at that plane strain answer. Can you see how much lower that is? Yeah, so just wanted to just demonstrate to you what happens if I make it plane strain. Can you see that much lower displacement because it's a lot more restricted to be able to move. Okay, so this is an important point. So that's you just visually see that I'm applying the same load. The displacement where the load's applied is now less. So what do you think is going to happen to the work? Okay, so that's it. So let's just go back to element type 6. So please make sure that you always double check that you are modeling the problem appropriately, because I might supply input file that is not 100% correct, and you need to just make sure that you can go through it and with confidence identify where things are not what they're supposed to be. Okay, so let's go back to this answer here. So we essentially see we resolve that same solution out. So we can actually go and see what is. You can go and compute this. Let me just show you here if I do this. Let's do it. Get it out of the way. 108 times 8, 22. You can see that answer here. I just want to make sure that when you see exactly the same, and you see this answer here, that you don't get confused. But you can see here, this is really what you expect to see. So solution, look at that, up to that digits, exactly the same. Okay. Bottom line, what I want you to do is, I want you to then say, okay, let's redo this problem. Create a Q8 push input file where we have a minus 73 newtons compression. So this one we pulled at 100 newtons, now we're compressing at minus 73 newtons. So we can run this one, store the solution as UM73. So this is the full displacement field that I'm storing there. Again, you can go verify the answer if it makes sense. What I'm doing now is to say, okay, fantastic. Let's solve it now as if we just applied 27 newtons. Okay, so here we pulled 100, then we pushed by 73. So the resultant is a 27 newton pull. So let's make an input file of 27 newton pull. Store the answer as U27. So that's what we're doing here. Okay, again, you can go verify what the answer should be. And what I'm now going to do is I'm going to plot here now the difference between the solution of the U27 pull and this U100 plus UM73 when I combine the two. So this is one FEM that I solved. This is the other FEM that I solved. I added two FEM solutions and we subtracted from the when we apply just 27 pull. And we can see what the difference is numerically 0. Can you see that? This is evident that this is all hunky-dory. Okay, another way to try and visualize this could be, for instance, instead of subtracting them, we could have divided the two, and we wanted to see essentially everywhere ones. So we could just say, we could have done that sort of division, and it's nans and awkward numbers where we had, you see what was it, where we had essentially zero boundary conditions. So that's not going to work if I do the division one. So those nans that you see here, it's because I'm dividing by 0. Okay, but essentially everywhere else you can see it's the answer is evaluated back to 1. So it's much safer in this case to rather just subtract, and you can see there are places where you have numerically 0. And so those are the ones that of course cause havoc, because those are indicative of not a computed solution, but a prescribed zero displacement solution. Okay, that's it. Okay, 100%. Now we're going to look at little investigations. Okay. So the first investigation we're going to look at is the following: make copies of all 3 previous input files, rename them to your choice, and then apply 100 Newton axial load, vertical load of 10 kilonewtons as 2 independent analysis. Do the third analysis with the loads applied at the same time. So we can do pull. We store the. What we're going to store is essentially we're going to get back U reaction force, von Mises, and the stress. So we're going to store the displacement, von Mises, and the stress. Okay, and you can go and check the input file and make sure that you agree with the loads that are applied. I can then say apply 10K vertical force. So this is then the solution that I store here after I run this. So let's make sure we run this properly. So this one is giving an issue there. This one is giving an issue because of that. That's hunky-dory. And now I can say here I'm going to have the input file that I pull and push at the same time. So let me just quickly show you. Let me just take the time to quickly go through this. Q8 bend 8, Q8 pull 100, Q8 pull 100 input file, Q8 bend 10K, and the combined one, pull and 20K. Yeah, that's it. So you can see the pull 100, that's fine. The vertical load, that is so this is the combined one I want to say. What is this? Oh, I opened the wrong file. Pull, where's the bend? Yeah, it's the bend. You can see all number 2's there, so this is all vertical. And we can see again the split that we have is 162, 31.6. So that's for the vertical loading that we have. And you can see that goes to 10,000. And then lastly, we have the combined one where we have some of the loads are vertical and some of the loads are axial. So that's what we see there. Beautiful. Okay, so those are the combined solution that we have. So this is making sure we're on the same page. And now we say essentially we've stored all these answers, we have all the solutions here. Now we can say what does the displacement difference look like when I take the combined load of 100 newtons and 10K vertical and I do the independent analysis and subtract that. I see beautiful, they are beautifully going to 0 as expected. What happens for the von Mises when I take the von Mises of the 100K and the von Mises to independent solutions? What happens if I subtract those? What do I expect to see? Well, I don't expect them to go to 0 at all. And the reason for that is we've done, to compute von Mises stress, we've done a nonlinear computation of the linear terms. So that's not going to be a linear superposition. Look at the difference there. The von Mises stress is vastly different. Okay, we're out here by 10, here we're out by another 10. So this is clearly not 0. So this is an important caution that you can't do nonlinear operations with the linear values that you got and then think that they will transform as linear superposition will hold for them. This is a really important point, cautionary point. I know it's something you've done in MW227, it's something you've done in MSY310. I'm just showing you here as a cautionary tale in case you've forgotten. This is not something you should be confusing. Okay, and then lastly, if I take the stress components, they indeed nicely cancel out to numerically 0. You can see it beautifully. Okay, so the stress components nicely. Why is that the case? Well, because essentially we've got the displacements that fully which linear superposition hold. From the displacements we take the derivatives, we get the strengths. That's all still linear, so that's linear superposition holds for strengths. I multiplied by a linear matrix, by just a constant matrix with linear terms in there. Well, let's just call it a constant matrix. The linear terms we can talk about now. And essentially that gives me stresses, and those stresses are then also the linear superposition will hold for that. This is why that happens, the reasoning. And here the wheels come off, because as soon as I start squaring the stresses and pulling square roots of sums of the squares and differences that are squared, this is not going to happen. That linear superposition holds for that. Okay, so linear superposition holds when things are on the line, but as soon as things are on a quadratic curve, obviously linear superposition does not hold for that. Okay, so this is hopefully clear. The next one that so this is some reflection questions. I'm not going to go through them. I've sort of already hinted to them what they are, and so you can really go and motivate for yourself, additionally to what I've just mentioned, why superposition holds for the stress components but not for the Mises. Okay, this is important. Now the next one I want to do is second investigation, which is important, is compute from the steel solution for any of the solutions. Compute from that steel solution that you've solved the aluminium solution. So change the Young's modulus from 210 gigapascal to 70 gigapascal and compare this against the aluminium solution. If I've solved it now using aluminium. So how do I spell aluminium? Aluminum. Okay. Sure. Okay, so anyway, that's that. And then after we've done that, we're going to ask the question, would this hold for Poisson's ratio? And we need to be able to say yea or nay with some confidence. Okay, clarity. So let's go. First off, we have the Q8 pull 100, so we're going to use this combined solution here. So this is what I'm computing here. I'm storing those values beautifully. And then what I'm going to do is, oops, my mistake here. This is the one I have. Okay. And then I'm going to have another input file, bend 10kL. So this is the bend 10kL. That's that one. So you can see the aluminium is in there. Boom, boom. And now this one, all I've changed is the Young's modulus. Everything else is the same to the previous notebook. All that is changed is the Young's modulus now. 70 gigapascal. Oops, wrong place. Now, yeah, okay. So that's it. And now we're going to do this, and we're going to put in here L as our solutions we're going to get out here. Just do it like that. And then we can see what's going on. Okay. Now we're going to ask ourselves what happens to if we have the U100 score 10K solution versus the aluminium solution. So this thing is 3 times stiffer. Okay. The steel is Young's modulus is 3 times higher than the aluminium. So I expect this displacement to be 3 times less. Okay, so if I divide the two, if I take this one, or let's start with the aluminium one and divide by the other one, because then we should see an answer of 3. And you can see right through beautifully an answer of 3, except for NANDs when we have 0 prescribed displacements. But that's exactly what we expect to see. The aluminium displaces 3 times more than the steel, 70 gigapascal versus 210 gigapascal. Hope your uncle. No problem. Okay. As expected. Obviously, this holds for displacements, this holds for stress components, it's not going to hold for the mimesis. And we understand why it's not going to hold for mimesis, because that's not going to be part of the linear transformation. Okay. Now we get back to this big question here. Will this hold for Poisson's ratio? Why am I cherry picking something like Young's modulus, and would this hold if I do it for Poisson's ratio? So let's go back to that input file and change it. And say, okay, so now this is not going to be aluminium, I'm going to change it back to Young's modulus. Okay. I'm just going to run it so that I can demonstrate to you that all is working. And now, oops, daisy. It's that one, this one run. Did I change the right file? And then this one, it's all ones. Okay, so that's just to show you this is all working. So the aluminium solution and this this aluminium variable is now still it's a steel solution. Okay, now I'm going to take that same file. I'm going to change, say, let's make the Poisson's ratio 0.0 for instance, or 0.01. Okay, so the one was 0.3. Originally it was 0.3, and now I'm going to make it 0.1. Okay. What happens if I now go back to my linear superposition here? Would this hold? And the answer is no. It will not hold. And those of you who are on board will know exactly why that's the case. So let's make sure this runs. Make sure this one runs. That looked like it ran. Make sure this one runs. And look at that. It's not a single scale factor here. You can see sometimes it's above, sometimes it's below. Some of them deviate quite a lot. Some of them deviate not so much. But it's definitely not just a linear superposition argument here. Okay, look at that variation. So this is clearly what we can see. The stresses can vary quite drastically. This is not part of linear superposition, because if I change Poisson's ratio, it's not like it's a factor 3 difference. Okay, and the reason for it is very simple and very clear. It's as the following. I'm going to see if I can open the PDF and get the Chapter 1 of my prescribed textbook, just to go back to the textbook and remind you of the constitutive equation. And this constitutive equation is linear in E. This is why we can cherry pick Young's modulus and say, oh, if I scale the Young's modulus, linear superposition will hold. This thing is clearly not linear in Poisson's ratio. There's a Poisson's ratio times a Poisson's ratio over 1. There's another Poisson's ratio that I multiply on top with. This is clearly not linear in Poisson's ratio. That's why it won't work. So you can always go and double check for any kind of thing that you want to try and change. Ask yourself, is the expression linear in that term? If it is, you can apply linear superposition. If it's not, you cannot do that. This is really what the crux of this is, so that you don't have to worry or be confused about stuff. You can always go and check, just look at the maths and just do a basic interpretation, and then you should be able to answer these questions with confidence, and also model with confidence, that you don't do awkward things, okay, that you can actually reason about things and reason them properly out. That's really the gist of what this notebook is about. Okay, so we've done 20 minutes, so there's chance for a quick other notebook that I can do, that we can maybe add into this block. Okay, but this is linear superposition. I wanted to make sure I spend time on it, although it's a concept that we've already solidified. It's really just making sure we go systematically through a couple of questions so that we're all on board. Okay, it also just gives a bit of breathing space for those of you who are still slightly behind. Thank you.